Welcome to RFIC design class. This is unit 3 and lecture 2. So in the yesterday's class we started passive impedance transformation. So just to have a quick review on what we did yesterday, passive impedance transformation is actually uh, used or using passive elements, how we are converting from a low impedance to high impedance basically for matching, and matching is required in order to have maximum power transfer from one stage to the other stage. So with respect to that, we looked at quality factor, and we stated that quality factor is something performance measure which says us how close to ideal and energy storing devices, and we defined the quality factor. Now we have written those things with respect to both RC and RL networks, and yeah. So after that, we have looked at the series to parallel conversion. So and we arrived at the series to parallel conversion values of resistance. Yeah, so we arrived at the values here. RP value, RP is RS into, so the parallel resistance value is RS into QS square, and the capacitance value remains same. And the same is true for even an RL, if I consider an RL network also. So that I haven't written here. So let me make a note that here. Yeah, so we observed that when we do series to parallel conversion, capacitance value retains, but the resistance value will be raised by a factor of QS square, and that is true when your QS is larger than 1. So one more thing to note down here is, if your Q value, say your Q value is 3 or 4, if it is more than 3 or 4, then the error what we, so we say that if your QS is larger than 1, then your CP will be equal to CS. Now if your Q value is greater than 3 or 4, the error which can occur here is some 10% error will come if I assume CP equal to CS. Now if your Q value is greater than 10, then the error percentage will be as small as 1%, right? So based on calculations we can say this. Yeah, so that is one observation we made, and then we started looking at a basic matching network. So before we proceed further, let me summarize. So any questions so far? Yeah, we'll be anyway we'll be discussing about matching networks today, whatever I started yesterday. So if you have questions in between, you can post here. So let me write this here. RP is equal to RS into Q square plus 1, and LP is equal to LS into, yeah, this we did not write, Q square plus 1 by Q square. This is actually true for, this is for series and parallel RL network, series and parallel RL network. We have done RC network, right? So now for that, RP is same, equal RS into Q square plus 1, and CP equal to CS into Q square by Q square plus 1. We have derived it in the same way, right? Yeah, yes. Now this is for series and parallel RC network, right? So if you look at the resistance, the real component, if you look at the resistance value, the parallel resistance is will be always larger, and that will be that magnitude is actually increased by Q square plus 1. But if you look at the imaginary, or if you look at the reactive components in general, I can say, so I'll make this statement in general so that we can no need to actually remember three formulas. In general, I can say the reactive component XP is equal to XS into Q square plus 1 divided by Q square, right? So this can be a formula in general, for both reactive elements. Now, one more thing we understand here, this equivalence holds good not over the entire range of frequency, but only for a very narrow range of frequency, or very close to the center frequency. That we'll see why I'm telling that this is valid only for a short range of frequencies, right? So so to summarize, what we have done is we spoke about quality factor, then we did a series to parallel RC and RL network conversion, right? So with this base, we are actually starting with some of the matching networks, right? So matching networks, as I mentioned before, it is useful for, yeah, it is for transforming impedance from a higher value to a lower value, or from a lower value to higher value, right? So we will start with this basic this circuit itself. So my need here is, I will just write it here. I'll consider this as, yeah. So my need is, I have a resistance, say I'm calling it as RL, and I need to match this resistance value to some other resistance value. Now, what I can do is, so I know now by using reactive elements. So what I'll go do here is, let me connect a capacitance here. Yeah. So if I'm connecting a capacitance here, now this is a parallel RC network, right? Now, since this is a parallel RC network, when I transform, or if I look for a, if I convert this into a series network, so as we discussed just now, when we do that conversion, the series resistance is actually smaller from the relation. We have seen that series resistance will be parallel value divided by Q square plus 1. So that is a condition, right? So can you tell me what kind of transformation this will lead? This will lead to, there is a resistance RL, and if I keep a capacitance in parallel to that, and if I look at the resistance from here, which is a series component, whether that, yeah, it will be a downward transformation. Yes, that is true. Now, so our idea is, or the need, a requirement is to convert a real impedance, a resistance to a resistance only. But since I have added a reactive component, I should cancel the reactive component finally, right? So I'm adding, actually I'm adding an inductance here, right? I'm adding an inductance here. So you can see that what I'll do here is, when I convert this RC, what it happens, L is already there. When RC will be converted into a series RC, parallel RC will be converted into series RC. So this is how the equivalent resistance will look like. Now this is same as a series RLC network, right? This is same as a series RLC network. And now if I write this value, say since it is a series component, I'll just write it as RS. Since I transformed into a series component, I'll write it as RS. Say this is L1, this retains as L1. Now this is C1, and I know that this can be written as C1, but that again depends on the Q factor. Now, I hope you are with me. Is a transformation value only for a specific frequency? Yes, I hope. I think Saurabh, you asked this question yesterday. Yeah, this is valid only for a specific frequency, or I can say for a narrow range of frequency. Why I'm telling so is, you can look at the circuit diagram. What I have written, what you are seeing now. You have a resistance RL. I want to convert that resistance into a lower value, right? So I did say a parallel to series conversion. So this parallel RC is replaced by a series RC here. Now, how this operates? I want only real impedance from here. Sure, Nikhil, I'm coming to that. Yeah, I'm coming to that. I can do that only with a numerical value. So what I'm trying to say here is, now when I converted, now what you have is a series RLC network. Now if I need my requirement is to transform my impedance into a lower value. So that means the real part of the impedance from here, the real part of impedance seen from this node should be only RS, right? Now how I can cancel L and C? L and C, or the series, the equivalent of a series RLC network is equal to the equivalent impedance of a series RLC network is equal to RS only when at resonance. right? We know that resonance is something at one specific frequency, the capacitive reactance will be opposite to your inductive reactance, right? So I hope you understand. We know that capacitance will act as a short for a low frequency, inductors capacitors will act as open for low frequency, but inductors will act as short. And again, for high frequency it is the other way, right? But somewhere in the middle point, or somewhere at one particular frequency, or for a very narrow range of frequency, we can say that this inductive reactance will be cancelled by the capacitive reactance, and that is how we say a series RLC network is in resonance. And when in resonance, the resistance will be pure, or resistance will be real. Is that point clear? Let me ask with Saurabh, Nikhil, because they have raised this question. So, Saurabh, did you get clarity on that? What I was trying to say? All right, Nikhil. Yeah. So what I am telling is the resistance. I had a resistance RL, and that is now RS. And by relation, I can prove that this RS is smaller. That means I could down convert, or I could actually transform the resistance value to a low number. But for doing the transformation, I have actually introduced. You can see I have introduced this part here. I have introduced this element, this L and C element I have introduced. Now, since I have introduced this, um, what I need is only a real part, right? But this LC should be cancelled. How it will cancel? It will cancel only at resonance. Now, at resonance, the circuit will provide a real resistance. Circuit will provide a real impedance. At the same time, the capacitive and inductive reactance will cancel each other. Yes. Are done for our analysis for a particular circuit, or are we actually changing circuit itself? I didn't get the question, Akshay. Mm.
So what I mean is, we are doing this transformation just to analyze the circuit, right? Not we are not actually doing hardware changes in a circuit.
Uh, Hardware changes in the sense, okay, you can mute Akshay. I'll clarify. Now your question is, say you want to transform 50 ohm impedance into 25 ohm impedance, right? If that is a scenario, we'll take up an example now. If I want to do this transformation and say I have 50 ohm impedance, now if I properly choose an L and C value, the impedance seen from here will be 25. That I'll prove it. Yeah. I think Akshay's question is whether these things, whether we will convert that from series to parallel to series. No, we will not convert. That is for our understanding, because when I make it as a series RLC, and when I say that at resonance, this will give only real value impedance, then you will understand. That is why I did this conversion. And through this conversion only, I can say that the resistance seen now actually is equal to a larger value. I hope you understand that, Akshay. Yeah. All right. So let me go ahead. So okay. So if you have noticed, I have written here the today's class. It is L matches. Now you can see the shape of this network. This LC is in the form of an L. So this is actually the shape. That is the reason why we call this as L match, right? Uh, yes, because adding LNC for reduction in impedance looks to be hard on an IC. Yes, Nagraj, for impedance matching, yes, we are doing this. Yes. Now, adding an external, including these components is hard. But in most of the times, say it all depends on the value what we are arriving at. When I say the inductance value or capacitance value, now see, whenever you draw a single line on a substrate, single line as a layout, single metal line, that itself will give you some inductance value. Right. So sometimes even bond wires, even small bond wires also will act as inductance. So for transformation, we definitely use these kind of techniques. Yes. Yeah, but it is hard. Yeah, so we should be careful. We should do it carefully, and we'll see. Yeah, when we start our circuit, from LNA onwards, we'll see how the output and input impedance are matched also. All right. Okay. So this is your basic, very basic matching network, and I'll call this as L match. And why we call this as L match is because of the reason, because of the shape. Right. So let us analyze this. So we know that this will happen, but let us still do a small analysis, and rest of the things we can write it as it is. Now, So this is the circuit. I marked this as RL, this as L1, and this as C1. If I look from here and if I write the impedance seen, I can say that the impedance seen is equal to R and C are in parallel. So I can write it as RL divided by 1 plus j omega into C1 into RL plus this inductance is in series. So it is j omega L1, right? Now, if I look at, so our, we are focusing only on the real part of impedance. So we wanted to know whether the real part of impedance is giving you a resistance value and what is the value, whether that value is a lower value or a higher value. Now, how to get the real part of this? So I can actually take the conjugate of the denominator. First, I'll take, yeah, I'll take LCM of this. Yes. So when I do that, uh, I'll take LCM and then I'll take conjugate and multiply and I'll finally result in a real part. So can you guys work out and tell me what is the real part of the impedance Z in? I think now I need to multiply this with 1 minus j omega C1 RL. Yeah, so you will get it as, yeah, some of you have written answer. So I'll directly take it. So the real part of impedance will be equal to RL divided by 1 plus omega square, yes, omega square RL square and C1 square, right? So this is the real part of impedance, or this can be further written as, so what is this quantity here? So I have a parallel RC network, right? I have a parallel RC. Now the Q factor of a parallel RC network is equal to RC omega. So if I write in terms of RL and C1, it is RL C1 omega. So this can be written as RL divided by 1 plus QP square, right? So the real part of impedance is this. So we know that when even we call it as real part of impedance. So this is in fact a series resistance, right? Or I will note down a point here that the RL is now transformed. RL is now transformed into a lower impedance or a lower value by a factor 1 plus QP square, right? So RL is now transformed into a lower impedance by a factor 1 plus QP square, that we have proved. Okay, now let us have a look at the imaginary part. So I have taken only the real part of this. So definitely when I do it, I'll get an imaginary part, and that imaginary part should be equated to 0, right? So how can I set imaginary part equal to 0? Can one of you unmute and tell me what are the imaginary part components? If some of you have done the analysis, you can tell me what are the imaginary components. Can one of you help me to get the imaginary part? So what I need to do here is I need to set imaginary part to 0. Yes. So all right. If you didn't get, I'll try to write it out. J omega L1. All right. Yeah. So there is a component j omega L1.
So is it r squared c omega by 1 plus r squared c square omega square?
What is that?
The imaginary component, sir.
I am trying to take the imaginary components from this equation. So
Okay.
yeah,
Oh,
have you
I
done that? So yeah, it is
uh,
okay. I'll try. I j omega L1, and the second component will be, this is real. Again, you will get minus. So yeah, you will get another component here, which is minus j omega RL square C1. That is from the real. Again, yeah, one more is plus j omega cube RL square C1 square L1. Right. I hope this is the imaginary part. J omega L1 minus j omega RL square into C1, and
yes, sir.
yeah, plus j omega cube into RL square C1 square L1 square. So this should be equated to 0, right? So there comes the point. So I told in the beginning that by adding a capacitance in parallel, I can transform this RL into a series RS, which is a lower value. But finally, to cancel the capacitance, capacitive reactance, I need to put an inductance. Now, let me write what inductance value I need to put here. So let me get an expression for L1 here. So I can j omega component will be I can remove, and then will be 1 omega square will be left leaving. So it is equal to RL square C1 divided by, this is 1 plus omega square RL square C1. Is it right? I have taken L1 from this part. So L1 is equal to RL square C1 divided by 1 plus omega square RL square C1. Now, if I choose a inductance value which is equal to RL square C1 divided by 1 plus omega square RL square C1, the reactance offered by this inductance will be cancelling the capacitor reactance. Or uh, if I write this in a little more better way, I can write it as RL square C1 divided by, we know that for a parallel RC, I can write the Q factor in terms of RC as omega RC. Yeah, I have written it is omega RC. So I can write this as 1 plus QP square. Right. So if you look at these two things, the real part of impedance. So let me write it again here. The real part of impedance here is equal to RL by 1 plus QP square, and the inductance value what I need to use here in order to cancel uh, the uh, capacity component is RL square C1 by 1 plus QP square. Now, denominator should have C1 square. Oh, yes. I think I missed. Yeah, C1 square is there. C1 square, yes. Yeah, is this right? Yeah. So if I look at these two expressions, the real part of impedance and also the inductance value, uh, yeah. So these are the transformed impedance, which is a lower value, and the inductance value is this one. Now, if the QP square or the QP value or QP square, if it is larger than 1, as mentioned before, I can write the real part of impedance will be only equal to RL divided by QP square, and L1 value will be equal to RL square C1 divided by QP square, right? Or how can I write this in a more compact way? Because QP is RL C1 omega, so it is equal to 1 by QP square, right? So this can be written as 1 divided by RL into C1 square into omega square. This is real part of impedance, and L1, if I modify, this is equal to 1 by C1 into omega square. All right. So I hope this is clear. So we have used a L match. So this is called as an L match to transform an impedance from a higher value to a lower value. So let me just elaborate, or just me explain this with a simple example, with one question. So the question will be like this: design a matching network. Design a matching network to transform impedance RL, which is a 50 ohms, to a 25 ohm impedance at center frequency, at a center frequency of 5 gigahertz. So design a matching network to transform impedance 50 ohms to 25 ohms at a center frequency of 5 gigahertz. Can you guys try this question?
So do we have to assume a capacitance value?
No need to assume, no, in this case. Do I need to
Oh,
assume?
no, sir.
So, so
Yeah, I have design equations with me.
Oh, in the R equation, C will be used. Okay,
Yes,
yes.
yes, yes.
So could you show the question, sir?
All right, okay.
Thank you.
No, no need to assume the value of C1, Akash, because
yes, sir, got it, sir.
yeah, frequency is given and resistance also is given. Okay, so how will you proceed with this question? So I have written the equations here, right? So let me directly take up that equation and check. So I know that the real part of impedance, I have obtained this equation as 1 by RL C1 square omega square, 1 by RL C1 square omega square. What should be that value? That should be equal to 25. Right. So that is what I'm expecting. The transformed impedance should be 25 ohms. Now I know the value of RL, omega is known, so this will actually give you C1 value. Now if C1 value is known, I can directly find L1. Now L1 is 1 by C1 in 1 by C1 into omega square. So can I get C1 and L1 values? Okay. Yeah, so if you go ahead with this assumption, or the equations what I have taken now, you will get C1 close to 0.9. Yes, Anirudh, your answer is right. I think you have taken the exact formula. I don't know. Let me come back to that. So this is equal to 0.90 some picofarad. C1 will be 0.90 picofarad, and if I substitute that, I'll get the L1 value as 1.12 nanohenry. Right. But before we use these simplified formula, because I have written the condition here, these two formulas are valid if your QP square is larger than 1, right? But how will I check whether my QP square is larger than 1 or not? So let me evaluate QP. This is for a parallel RC network. So QP is equal to RL into C1 into omega. And if you evaluate QP, you will get QP close to, can I get the QP value? QP is 1. Okay, I think I am getting QP close to 1.413, right? So since QP is 1.413 or 1.43. Okay. So since QP is 1.413, I cannot say that QP square is very large than 1, right? So I cannot make this assumption, or as I told before, if your QP is greater than 3 or 4, that will result in some 10% error, and if your QP is greater than 10, it will result in almost 1% error. Now since your QP is 1.413, this may result in a little more, a large variation. So I cannot actually use these formulas here, because QP square is this is not valid. QP square is not very large than 1, right? Or one more way how you can check for the QP is, you can directly get that from the transformation ratio, because you have written that approximate value, approximate QP, you will get it from here, because we know that RP is equal to QP square into RS, right? So what is QP? QP is actually under root of RP by RS. This is approximately I'm telling. RP is actually 50 and RS is 25, which is root of 2. I think we are getting a close value, right? 1.414. Yes, Sarvesh. So we have to use the formula what we have written now. So with that, we need to calculate the new value. So I need to comment here that since QP square larger than 1 is not valid in this case, since this is not valid, I need to take the real part of impedance as this formula, RL by 1 plus QP square, and so I'll get C1 value from this. Using that C1 value, I'll substitute for L1. L1 is RL square into C1 divided by 1 plus QP square. So your L1 value will be close to that. Yeah. So can you guys work out and tell me what is R1 and C1 value? Yes, so this will result in a C1 value which is equal to, what is C1 value here? Yeah, 0.636 picofarad, and that will give an L1 value of 0.796 nano Henry. Yeah, 0.63 and 0.79 nano Henry. So now the equivalent circuit in the sense, the circuit which will give me this transformed impedance is this. So this is a circuit what I have. This is 50 ohms. This is 0.63 pico and this is 0.79 nano. Now the impedance seen from here is actually equal to 25 ohms. Yes, go ahead. Who is having a doubt?
Sir, here, like,
Yeah.
I think we get QP square equal to 1 at some point. If I'm
In
Yes, sir.
which case,
QP we get as one, sir.
where I'll get QP as 1?
the real part of Zn it becomes 25 ohms, sir,
Yeah.
and RL is 50 ohms.
Yes.
So when you cancel, it becomes 1 plus QP square equals 2. Hence, QP square equals 1.
Okay.
So then, how are we get us achieving that assumption of QP square very much greater than 1?
No, it is not greater than 1, no?
Okay, okay.
QP square greater than 1 is not valid. That is why I have taken this, right?
Okay, sir. Yes,
Yeah,
sir.
our QP value is very close to 1. It is 1.413.
Okay.
Yeah,
Thank you, sir.
yeah, all right. Yeah. I hope that is clear. Now can you tell me how to transform to a higher value? Now I have 50 ohm. I transformed into 25. So how to transform to a higher value? Using the same type of L section. So this is an L match. We call this as L section topology. So any idea how we can get a transformation to an up, like how we can upward impedance transformation? How is it possible?
So what if we place the capacitance in series?
And
Capacitance
the
in
inductance in parallel.
all right, capacitance in series, you mean to say like this
Yes,
in
sir.
this? All right, put C in series and parallel. Okay, if I put C in series and an L parallel, yeah, definitely you will get upward impedance. Yes, that is true. Now before doing that, let me take this. I have an impedance RL here. Now the same L section I'll just place in the other way. So I'll put L1 here and I'll put a capacitor here. Whatever you told, keeping C in series is also right. I'll come to that topology as well.
Okay, sir.
Yeah. So this will also give you a transformation. So let me take this as case 2. I hope I put the other one as case 1. Yes. Now this is okay, let me mark it as RL and this as C1, and you can clearly see that this is again in the shape of an L, and we call this as L section topology. So what I'll do here is that I'll just transform this. I have a series RL here. So how does the transformation work? So I have a series RL here. Series RL can be converted into a parallel RL. So what I'll do here is I'll draw this as RP. Now this is an inductance and I'll place the capacitance as it is. Now what is the result? Resulting what I have is a parallel RLC. Again the parallel RLC at a resonance will provide an impedance of RP. The same thing works. So again this circuit works for a narrow range of frequency or for a frequency. It actually worked perfect for a single frequency at resonance, but at least over the narrow range of that. So this is how it works. So I can directly write RP. I know no need to analyze this. I can directly write RP as the QS square plus 1 into RL, which can be approximated as QS square into RL. And that will be, yeah, if I do that, that will result in the equations which is L1 square omega square by RL. And L1 can be taken approximately equal to L1 itself, right? So from the previous transformation or the analysis, we can deduct these formulas. So this is basically acting as a upward impedance transformer. Yeah, Sarvesh, yeah, I am seeing the response of all of you. Like I'll summarize all the cases here now. So this is an upward impedance transformer where this is a downward impedance transformer. Right. Probably now you would have arrived at the conclusion that with for this upward and downward, if I use LC in combinations in different ways, I can actually get two types of upward transformation and two types of downward transformation. So let me just summarize the 4 L section topologies here. So the first one is I'll have a resistance RL. I'll put a capacitance here. Now to eliminate, so capacitance is added to transform the resistance value to a lower value. So to a lower series resistance, this is, I'll put it as RL, this is C1. and L1 is added actually to cancel C1. Now if I look from here, the real part of impedance will be lesser than RL. The real part of impedance is lesser than RL. That is what this transformation will give you. This is your downward impedance transformer. And now similarly, if I do in this form where I have a resistance RL here, and in place of C, if I put inductance L, so this is L1 and this is RL, and so L1 is actually so this is parallel RL. Now L1 is added actually to transform RL to a lower series value, and C1 is added to cancel it. So this is C1. Now if I look from here, the real part of impedance, this also will be less than RL only, right? So these two are called as downward impedance transformers. These are called as downward impedance transformer. So in this case, C1 C1 is actually transforming, the C1 transforms RL to a lower series resistance RS, and this L1 actually cancels the C1. Similar is actually the case of the right side circuit also. So in a similar way, if I, as you guys suggested, yeah, if I have a resistance here which is RL, now if I add an inductance in series L1 and a capacitance here in parallel, this will of course give you a value real part of impedance greater than RL, right? And as you guys suggested, I have a resistance RL. Now I'll put a series capacitance and then a parallel inductance here. Let me mark this as RL C1 L1. Now the real part of impedance will be greater than RL, right? So these two are upward impedance transformers. So here, yeah, in this case, L1 transforms RL to a higher parallel resistance, and C1 cancels L1. It is otherwise vice versa in the case of yeah, these circuits. So this is your C1. I hope this will give a clarity on the L section topic. So we have analyzed the first one, and the rest of the things we have written by the previous analysis what we have done, right? So this is called as L section topology. Now if you have doubts you can ask, otherwise what I'll do is I'll show a quick simulation on this. So can you think of any drawbacks of this circuit, L section topology?
If you want to transform some circuits from very high resistances to lower resistances, then you'll need a very high Q, which is not implementable.
Okay, why it is not implementable? Why very high Q?
L and C values will be it won't C will probably be very low for you to
Okay, all right. Okay, let us see that. Frequency of operation will be high for high Q. Okay. Resonance is needed to get real values of impedance. All right. Okay. So I'll come back. I'll come back to this. Before that, let me. I hope you can see the screen now. Right. So the screen, what you are seeing now is having the same circuit. I have a resistance here of 50 ohm impedance, and that has to be transformed in the same example what we have taken, what we have done now. So same 50 ohm impedance should be transformed into a 25 ohm impedance. Now, since I need to transform from 50 to 25, the Q factor is very close to 2. Q factor is root of 2, which is close to 1. So then I have to go with the exact formula, and that when I use that, I arrived at these capacitors and inductance value. The capacitance value is 637 femto, which is 0.63 pico, and inductance is 796 pico, which is equal to 0.796 nano. Right. So I have used the same inductance and capacitance value. Yes, Anirudh, I'll come back. Unnecessary frequency dependence. Yes. Let us discuss on that. So before that, let me show the simulation and see how this LC or this L match. So what you are seeing now, this is actually of the shape of L, and this is your L match. How this L match is transforming this 50 ohm impedance to a real impedance of 25. So to do that, I'll launch ADL. I launch ADL. I already have a session which is saved. So I load the same state. Yeah, so what I did here is, okay, I did not explain what I have here. You can see a port here. I have used the same port even to do the other kind of analysis in the first, I think in the first unit we have used this. So let me just go to this port. You can see the resistance offered by the port. The resistance offered is 50 ohms, and yeah, there is no reactive components, anything is there. Yeah, so you can see that there is a source type which is sine. I kept it as FRF as a frequency name and a frequency value, and amplitude is PRF, and those things are set in the ADL window. So if I look at this ADL window, you can see that FRF is kept as 5 giga. I think I have given the question with omega 5 giga only, right? Yes, it is 5 giga. And I'm giving you an input component of minus 20 dBm is my input signal component. Now, yeah. So if I since I want to perform since I want to evaluate the real impedance here, what I'm doing is I'm doing an SP analysis. So SP analysis will actually give you will help you to measure yeah. So to perform SP analysis, I need to select the port, and I need to keep the sweep variable as frequency, and I'm varying from 1 giga to 10 giga. Since the frequency of operation, what I need to look is around 5 giga, right? So I'll just click it. I'll show what all things can be evaluated from this SP analysis. So I have given a run, and yeah, so the simulation is successful. I'll go to results, direct plot, to the main form. Yeah, so in SP analysis, you have actually the provision to measure a lot of things, right? So what I'll measure is I'll actually measure the Z11. I'll measure the impedance. Z11 represents the impedance seen from this side. So I can get this is Z parameter basically. I can get the magnitude phase dB20 real and imaginary. So what I'll do here is I'll check the real and imaginary component. So what I know is this should transform to a real impedance of 25 and with an imaginary component of 0 or a lesser value, right? So if I press on Z11, I'll get a plot. Sorry for this I leave in between. Yeah, so you can see that there is a plot here, and if I put a vertical trace around 5 giga, at 5 giga the impedance is close to 25. So if I keep this as yeah, it is 24.98 is the real impedance. So this is real component. Let me check the imaginary component also. So imaginary, if I click and I plot the imaginary component at 5 giga. Yeah, so at 5 giga your imaginary component is less. Yeah, you can see it is close to 8.4 milli, which is close to 0 actually, right? So this is the real component and this is the imaginary component obtained. So what we did here is we use this L section topology, which is an LC element, which transformed this 50 ohm impedance into 25, right? So you can try all the other section topologies with respect to various frequency. Yeah. Now I'll just conclude the session with this, and tomorrow we'll discuss further. So the main drawback of this L section topology is you can see that we have the provision to choose this L and C, right? We have the provision to choose both L and C. We have, or I'll say we have the option to choose only L and C. That means there are only 2 degrees of freedom. We have freedom to choose only 2 things. Now what is the problem here is, once you know the impedance transformation ratio, that means now you know that I need to transform from 50 to 25, and 50 to 25 will directly give you the Q factor value very close to 1.4, right? So once your impedance transformation ratio is known and once your resonant frequency is specified, the Q factor is automatically determined, right? You do not have a control over the Q factor. Right. That means if you want to have a different value of Q, that is not possible with this L section topology. Since the Q factor is automatically determined by the impedance transformation ratio at a particular frequency of operation, different values of Q is not possible. Right. Since this L section topology is leaving you with only 2 degrees of freedom, so we will look for some other matching networks which will allow you to work for a different value of Q. So that we'll see from next class, right? So I'll be winding up today's session now, and if you have questions, you can ask.